Good evening and welcome to a new food4Rhino webinar. And welcome Max Zorn. Max is a researcher and doctoral candidate at the Department for Computing and Architecture of the Institute for Computational Design, University of Stuttgart. And well, Max is also an architect, computational designer, and he's been developed Opossum together with his team, again at the ICD Stuttgart. We are very geared here to learn more about Opossum. This is a Grasshopper plugin for single and multi-objective optimization, and also for design space exploration. And yeah, I met Max some months ago in a conference, and we were talking about this very nice plugin, and I offered him the possibility to do this webinar, and he kindly accepted. So, Max, many thanks for being here, and we are glad to see what you're going to show us. To the audience, please use the chat as much as you want. I will capture your questions for the end of the webinar. So there will be like 40 minutes presentation and live demo, and then questions. And as always, we are recording this session. So probably between tonight and tomorrow, it will be available on our YouTube list. And yeah, Max, welcome again, and please start with your presentation.
Thank you. Thanks, Carlos, for having me, and welcome everybody. All right. So tonight's topic is architectural design space optimization with Opossum, and as Carlos already mentioned, we're developing this plugin at the Department for Computing and Architecture at the University of Stuttgart. It's initially been developed by my professor, Thomas Wortmann, and I kind of took over when I started my PhD. So let me begin with explaining to you a little bit what architectural design optimization is and what it is about. So when we design a building today, and hopefully all of you do that, we do it, or we can do it in Grasshopper, which means we can build parametric models that not only depict one single solution or design, but actually a multitude of different designs. And this set of all possible designs we can call the parameter space. Now what we can do is we can use something like a simulation, like FEM or building performance simulation or something, to quantify the performance of our designs, right? And so a design can be good or bad in that regard. And now this space we call the performance space. And when we now look for designs that fulfill some certain requirements or perform well, right, we don't have to manually search these spaces, but we can use or we can formulate an optimization problem and then use algorithms like the ones that I implemented in Opossum to search the design space, this parameter space, and the associated performances algorithmically and very efficiently. So architectural design optimization is the guided algorithmic search for well-performing designs. When we do optimize, there are two types of optimizations that we want to talk about. It's single and multi-objective optimization. Oh, I'm sorry for the German title. So single objective optimization on the left-hand side is somehow easier to solve. You only have one objective. The results are kind of simple to interpret. What I mean with this, I'll show in a second. And we find a well-performing solution and optimum. Multi-objective optimization, on the other hand, is when you have more than one objectives. They are harder to solve and harder to interpret because we'll find a set of potentially equally good points. I don't know what happened here. Anyways, so a single objective problem could be formulated as I want a cheap building, right? So you somehow measure the cost for your buildings, and the building with the lowest cost associated would be your optimum, your single cheapest building. However, a multi-objective question could be, I want a cheap building that is also sustainable, right? And how, as we all know, timber is more expensive than concrete. So there's this trade-off now between the price of the building and maybe its global warming potential. The goal of multi-objective optimization now is to find those points that cannot be better in one objective without compromising another. So, for example, a building that is very, very cheap, but also bad for the environment, in this scenario is equally good as the most expensive building that has the least global warming potential. And this set of optima is called the so-called Pareto front. And I want to stress this because every multi-objective optimization problem, or also the algorithms behind your plugins, when you use multi-objective optimization, that is what they're gonna solve for. They're gonna try to find the best Pareto front. So a set of solutions. Exactly. And while we are informed, let's say, about the single best solution or a ranked list of solutions in single objective optimization, multi-objective optimization informs us of the trade-off between the objectives that we chose. So in practice, there's this study by Thomas and some of his colleagues where they interviewed a bunch of architects and designers and researchers and asked them how many objectives they typically optimize for when doing architectural design optimization. And you can see that actually only if like a third, or actually less than a third of the people use single objective optimization. Also, quite a lot of people said they're optimizing for more than 3 objectives. Typically, when there are more than 3 objectives, we stop talking about multi-objective optimization. We start talking about many objective optimization. And most of the algorithms that are implemented in Grasshopper plugins are not suitable for solving these problems, right? So you should draw a boundary when you optimize at like 3, maybe 4 objectives max. And I'll come back to that again. Okay, draw conclusion, don't optimize for more than 3 objectives. Formulating a proper multi-objective optimization problem with 2 objectives is hard enough already. Okay, so, but in architecture, we often think about our problems as characterized by more than one objective, right? Like this example of the building that should be cheap but also sustainable. So the question arises, if I have multiple objectives, should I still do some version of single objective optimization, or should I do multi-objective optimization? So the first question that we have to answer is, are there competing objectives? So objectives where if one gets better, the other gets worse. If no such competing objectives exist, we look at whether or not they scale similar. And if they do, we do single objective optimization with a weighted sum. And if they don't, we can do single objective optimization with a weighted product, where we just either sum up or multiply the different objectives. However, if there are competing objectives, another question then is there a limit? So for example, is in this scenario with the expensive or cheap buildings, right? How expensive, or like what can I afford? How expensive can the building be? Because then, I'm looking basically for the most sustainable building at a given price. We can, to solve these kind of solutions, we can use penalty functions and then formulate a single objective optimization problem that way. there are no limits, then we need to ask ourselves if we want to understand the trade-off. So how cheap can I build with a given sustainability index, or how sustainable can I be with a given budget? If I'm not interested in these trade-offs, then I can again basically formulate a single or a single objective problem with some scalarization. But if I want to understand these trade-offs, only then I should really do multi-objective optimization. So again, MOO, I know it's easy to just connect multiple objectives in Grasshopper, but these algorithms really are only suitable if you want to understand, if you want to learn about the trade-offs between different objectives in your design. Okay, I quickly mentioned weighted sums, weighted products, and those penalties, right? So basically, we're going to look at this later in Grasshopper too, but these are methods to just combine our different objectives into one more abstract objective that we can then optimize for. And with the soft constraints, that is also a way of guiding the algorithms, right? Lots of the objectives that we actually look at in architecture have some norm behind them, right? Like a slab cannot exceed a given deflection and so on and so forth. Of course, we could use hard constraints and say every design that exceeds this given constraint is unfeasible. However, this is for the math behind it and for the algorithms themselves, it's not so easy to then find really the good areas of your performance space, right? If you just arbitrarily throw out points. So it's better to use these soft constraints and basically guide your algorithms towards the solutions that you expect. And we're going to do this later, or I'm going to do this later in Grasshopper. Okay, there are many different algorithms. I mainly want to talk about meta-heuristics versus model-based. But before we're diving deeper into it, you can ask what's the best optimization algorithm. And if you actually Google optimization in Grasshopper, there are many entries in the different forums where people are asking for advice on which algorithms to choose. But unfortunately, there's the no free lunch theorem that says that over all given optimization problems, no algorithm performs better than any other, right? So, which also means not better than random search. So over all types of optimization problems, whether this is, I don't know, flight scheduling or some abstract math or architecture, we cannot just say a algorithm is the best. But it depends on the problem and on the problem class. So in our case, so in architecture, right, we most often don't actually know our function that we want to minimize. So a typical optimization problem would be formulated as such, right? You have some function f of x that needs to be minimized. For example, with the cost, right? But typically we don't have a mathematical representation, but more likely a Grasshopper script where some simulator calculates this f of x without the optimization actually knowing what's happening here. So we call this actually a black box optimization problem, where everything that needs to be minimized is unknown to the optimizer itself. And in order to solve such black box optimization problems, there are basically two strategies. One is exploitation, and the other is exploration, where in the exploitation scenario, you start at a given location and you just look in this certain area until you find the best solution in this area, right? But if you only do this, this could mean that you miss the best solution. Exploration, on the other hand, is it tries to maximize the space coverage, right? So if we think back about these spaces I talked about in the beginning, in exploration, we really want to set out and look at as many different points as possible. And we just hope that somewhere we find points that are better than others. And really what the optimization algorithms then do is they switch between these two strategies, right? So they're going to explore, they're going to find areas where they, think it's nice, where the performance is good, and then they try to dig deep, and exploit this region to then find the best point in this region, right? And the more exploration you do and the more steps of this you do, the less likely you are to find so-called local optima, which are points, let's say maybe close to here, that is already quite good, but a point maybe over here would have been a lot better. And there are different approaches in doing this. So the three most basic, and I'm sorry if this is a little too naive for some of you, but basically we can look at three different model classes or algorithm classes: meta-heuristics, direct search, and model-based optimization algorithms. So meta-heuristics are all types of algorithms that are more or less inspired by nature, right? Something like the genetic algorithm that is implemented in Galapagos, or NSGA2, very, very popular optimization algorithm. And basically they're stochastic search engines. They have a very smart way of doing random search, right? So basically you have a random strategy, you try to inform this random strategy by your observations, and steer the algorithm towards good solutions. But at the end of the day, they maintain, or they are stochastic, and are very dependent on this type of smart randomness, let's say. There's direct search. Direct search is basically a deterministic search strategy where you sample the entire space and you keep dividing the space into smaller and smaller bits. And you are very likely to find an optimum solution if you have forever to solve your problem, right? If you have infinite time, you will find the optimum. Yes, and then model-based optimization algorithms, they can be either stochastic or deterministic. Sometimes they also alternate in their strategies. And what they do is they build so-called surrogate models. This is like a machine learning model in the background, and they inform their optimization strategy with this machine learning model. And they basically try to model this unknown function in the background to the best of their knowledge and try to optimize on this model of the simulation that they built, which is then iteratively refined step after step with every observation that we draw from the simulation. So these three strategies can be used. There are also more, and I'm sorry if I didn't explain all types of algorithms, but let's focus on these three for now. And there are also plugins in Grasshopper that basically include these three types of algorithms. So in Opossum, we have both meta-heuristics and model-based. And quite specifically, there's one model-based algorithm that my professor developed during his PhD that seems to perform very well. So to look at this a little more figuratively, in the seed map, you can see the little black dots. These are global minima, so global optima. They're all equally good. And you can see how the different algorithms have different strategies in finding this. So in direct, you can see basically it built this grid, and then it subdivided the grid further and further in the areas where the performance was high. Simulated annealing goes into these kind of directions where it like cools off or heats. Then we have particle swarm where I restart this, I think you can see how the points kind of start to flock around areas with good solutions. And then we have RBF opt that in the beginning samples very vast. Some tries to find points on the entire surface. And then basically, because it then already has a naive understanding of the space, can search very targeted in good areas. And then we have the one that the Galapagos algorithm, and you can see how it just keeps going and going and kind of misses the optima until now. It found something. Well, basically all the others are simulated annealing is also still going, but the others are already finished. Okay. Earlier I said you cannot say which algorithms perform best. This is not really true. It's just true over all problems, but luckily we can define our problems ourselves, right? We're in the architecture domain. So what we do is we do a lot of benchmarking where we test different algorithms on different problems. So this is a study again by Thomas from 2019 where he tested single objective optimization algorithms on a huge set of different problems from architecture. And you can see that RBF opt, this is the algorithm here, performed best. And that direct was also good, and so on and so forth. Here is a newer benchmark that I published earlier this year. This is now multi-objective optimization. And again, so this blue line here that goes up very rapidly and then kind of dies down, that is RBF mob. This is the multi-objective version of RBF opt. So you can see that within very few iterations, actually, we achieve very, very high results, actually higher than any of the meta heuristics, so NSGA 2 and 3 achieve over the entire length of the benchmark. Interestingly, this other purple line here is another model-based algorithm. It's a Bayesian optimization algorithm, TPE, that is implemented in Tuni. And I wanted to stress this because we have many benchmarks now, many data sets that repeatedly show that on these more expensive problems, the model-based algorithms just outperform meta heuristics. And again, this is true for RBF mob and TPE. Another thing, earlier I said the meta heuristics are stochastic, right? So if you run the algorithm multiple times on the same problem, you might end up with very different results, right? You might be lucky. So this is what you see here. These box plots show basically the worst run, the best run. The green line is the median run. I ran those algorithms multiple times on the same problem. And you can get very lucky with these meta heuristics, but you can also get very unlucky, whereas those model-based algorithms are more robust, as we say, right? So you get like consistently good. Okay, to recap, model-based algorithms are good for expensive problems with small budgets. So if you cannot afford running your algorithm for tens of thousands of iterations, maybe your daylight simulation takes a couple of minutes and you don't want to wait 3 months for your result. So you have a small budget, you're very good to go with model-based algorithms. Generally, single objective optimization is good if you want to find an optimal solution, and multi-objective optimization is good if you want to understand trade-offs. Okay. Now, what if you don't like the optimal result from your optimization? So we've done optimization, we have our results, and now you change your Grasshopper script and you're like, hey, this building, I like more. Of course, you could now run the simulation again and do everything by hand. but we can learn from our observations that we drew from all these simulations that we've done during optimization and build machine learning models that then predict this performance much rather than you having to wait again for minutes at times for the simulation result. And so then you as the designer are actually being informed about these performances much rather than just the algorithm, right? And you can do this interactively and visually, and we have this beautiful little component, the Performance Explorer. It's the Opossum with the cool shades that actually allows you to do this interactively, and I'm going to show you in a bit how that will look like. Okay, before we jump into the demo itself, I want to say a few words about the model that I'm going to present because I'm not only researching optimization algorithms, I'm also part of this larger research effort that we started this year at the Institute in collaboration with a couple other institutes at the University of Stuttgart. So the project is called the Universal Timber Slab, and we're developing a new timber building system, as the name suggests. The project is funded by the EU, and yeah, like I said, it's conducted at the University of Stuttgart. So my colleagues Renan Brandini and Gregor Neubauer were very nice and built this abstracted Karamba model of our building system. So the basic idea is in this new building system that all forces will basically follow timber lamellas from column to column, and yeah, so we're gonna look at this particular abstraction of our system. Later, we're gonna vary the column placements and the slab thickness, and we're gonna look at the displacement and volume. Okay, so if you're interested in how this particular research project is going, then you can follow us on LinkedIn and Instagram, or subscribe to our newsletter. Here you can see again this idea of the lamellas, which we're going to simulate with Karamba today. Okay, then thanks for listening to this very quick presentation. Opossum itself can be downloaded both from food4Rhino or directly through the package manager in Rhino. And you can obtain a free license at opossum-optimizer.com. Yes, I'm also going to show you our website very quickly. So here you can see our website. You can get the free license by just entering your first name, last name, your institution, and an email address. Your licenses are they don't expire. You can do any type of work with them. Yes, exactly. Okay, so now let's look at Rhino Grasshopper. I think we're going to do the Q&A at the end. So
Yes.
Awesome. Okay, like I said, we have this little model of a irregular slab. For demonstration purposes, I now use a gene pool that you all know, as well as sliders to vary the column positions, and the slider for the slab thickness. Exactly. So we have our little Karamba simulation. I do calculate the volumes. So basically, we can look at the displacement, the volume, and the structural height. Earlier during our little presentation, I said that multi-objective optimization is only good if you have competing objectives. So now how do you know whether your objectives are competing or not? Either you just know, right? Some relationships are very trivial. Quite generally, super light slab will have a high displacement, right? If the thickness is almost zero, then it will not hold. Some other relationships are more complex. So what you can do is you can initially sample your space or your Grasshopper solution, just calculate a bunch of different designs and calculate a correlation matrix, right? Where you can calculate exactly those relationships. And I've done this for our example today. And we can see that, yes, indeed, our volume and our displacement are negatively correlated, which means that typically if one goes up, the other goes down, right? Or if one becomes better, the other one becomes worse. So the thicker slab has the smaller displacement. So theoretically, this would be something that would be suitable for multi-objective optimization. Okay. So you find Opossum in the utils tab under parameters. Again, there are two components, our regular Opossum component and the performance explorer. For now, we want to grab the regular component. You can see we have three inputs. We have variables, simulators, and objectives. So variables are all those parameters that you want to change during your optimization. So for us, it's the X and Y position of the columns and the slab height, right? And because it's very tedious to manually connect all these different sliders, there are two ways of doing this a little bit more automated. If you right-click on variables, there's the option to link all variables. If you have marked, so all variables would now be all sliders and all gene pools on your canvas. If you have marked a selection of sliders and gene pools, you can also say link selected variables, and it will automatically link those to the variables input. Okay, let's move to the other side of the screen again. Okay, so for now, let's start with like a single objective optimization run. And generally, I'm interested in slabs with low displacement today. So I'm going to optimize for now just for displacement. And for those of you who know their structure, wait, before we actually start doing this, the first time you double click, so basically to interact with Opossum, you double click the component. The first time you do this, it will prompt you to enter your license, right? So you just copy paste the license you got from the website, and then this window will pop up. Your main interaction will be with the optimize tab. Here you can choose minimization or maximization. You can choose different algorithms for a single objective. In Opossum, this is only RBF opt and CMA-ES. CMA-ES is also a meta-heuristic search strategy that turns out to be very good if you have many runs, right? So RBF opt might at one point just say, you know what, this is good enough. We're going to stop it here. Whereas CMA-ES will just continue optimizing. So if you have thousands or tens of thousands of iterations, because your simulation is very fast, you can very well use CMA-ES. Okay, then there's a settings tab that allows you to, for example, set the maximum iterations. It also allows you to write a text file with the results on the fly. There's an expert tab where you can manually set some more settings. There's also the link to the RBF opt documentation if you hover over this window, where you can find more of the algorithm settings that you can vary here. And then there's the results tab, which is empty as of now because we didn't actually do anything yet. So back to the optimize tab. When I hit start, Opossum varies our input variables. We observe this objective and we try to minimize this objective. Okay. already we found a really low displacement with just 0.6. So I'm going to stop the optimization for now. And now what I wanted to say, if you know your structure, right, you will know that you will find somewhat thick thick plates if you optimize for displacement alone. Going back to the results tab, now all the results are here. If you want to explore the different entries, you can double click on any given solution and it will update your Grasshopper canvas, and you can see how it changes in Rhino 2. Okay, if you want to save this, if you didn't save the text file, you can with Control A mark everything and copy it, Control C, and paste it either to Excel or a text file. Okay, if you hit save and close, the results will be saved in this window. If you just hit close, you will lose all your results and also all the settings that you've done. Okay, now coming back to the multi-objective instance. So maybe we're not interested so much in the most, or in the slab with the least displacement, right? Because maybe there are norms that say, okay, your slab cannot displace more than 5 centimeters, right? But maybe I'm also interested in my global warming potential, or like just the material, the weight of our structure. So in this case, we can also look at the volume. And as we've seen before in our correlation matrix, the volume and the displacement, they're competing objectives. So this is a totally valid multi-objective optimization problem. In order to add a second objective, I can just I can do it again, press Shift and connect a second objective to Opossum. It's also, maybe that's a fair hint, you should always connect Opossum to a number container. The output of some of the components, like the results from an addition, is also a valid connection to Opossum, but sometimes it misinterprets a 0 as a not a number and will throw an error. So if you see expected double got NAM as your error message, then it's most likely because you didn't connect a number container as your objective. Anyhow, I now connected two objectives. The selection of algorithms when I open Opossum now changed. It says RBF mob now, not RBF opt, and there are also a couple other algorithms that you can choose from now: NSGA2, the particle swarm, MoEID, and an ant colony algorithm. We're going to stick with RBF mob for today, and we're also not going to change any of the other settings. So I'm going to run this now. Again, we're trying to minimize our volume in our structure and at the same time also minimize the displacement in the structure. Like I said, multi-objective problems are harder to solve. They demand more budget than single objective problems. Yes. Okay, cool. For demonstration reasons, I'm just going to quit it at 80 now. Okay, and what also changed now is the way the results tab looks. So it gives you the rank, it gives you a value that is called volume, giving you the objectives, objective 1 and objective 2, and the associated parameters. The rank is the Pareto front. So earlier, when I drew the Pareto front, right, the best front is the front with rank 0. It's where really all the best points are. Then the second best front is the rank 1, and so on and so forth. And on this Pareto front now, you will find points that have very low volume but a high displacement, but also points that have larger volumes, but little displacement, right? So this is now exactly the trade-off that I was talking about. So this particular instance has a volume of 40 and a displacement of 0.7. And this first instance had a volume of 7 and a displacement of 147. And to the optimizer and to a multi-objective optimization, or as a multi-objective optimization problem, those 2 points are equally good, right? So this is the lightest structure with the lowest displacement. So there might be equally light structures but they will all have worse displacement. And this is the structure down here with the, here with the lowest displacement, but the least volume for this given displacement. Okay, and now, Opossum will present to you many different points, and it's up to you which one of those solutions you actually like. You have to manually explore this. And again, this is what I meant earlier with like learning about the trade-offs. Okay, last version that I talked about earlier was scalarization. So as I mentioned, maybe we're not interested so much in the exact displacement in our slab. Maybe we're just interested in the fact that our slab cannot exceed, for example, 5 centimeters. And in this case, we can set this displacement as a limit, right? And then we can use our volume actually as the objective to minimize. So we're now looking for a slab with very little volume, but we're going to penalize all those solutions that do exceed our target displacement. And you can use different functions to do this. You can do this linearly or exponentially or logarithmically. But the basic idea is that you calculate a penalty factor based on how bad your solution exceeds your target, and you combine this with your other objective. So if we are optimizing for this now, the optimization is going to go in a little differently, right? So we're actually looking now, all the optimum solutions will actually have a displacement that does not exceed our target, and they might just vary slightly in weight. Okay. So going back to our results, you can see this here, right? So on the right-hand side in this panel, the displacement is just below 5, and the structural height now is 18. Earlier, when we only optimized for displacement, the structural height was 24. Okay. So the last 2 minutes, I want to take and show you this design space exploration tool that I mentioned earlier. So, okay, now that we have our data, our results, maybe clicking in this table is not so intuitive, right? So you can grab the other Opossum component, our Performance Explorer, and connect the results output from Opossum to the input in the Performance Explorer. And again, double-click this component to start the visualization. But before you do this, there's another input to the optimization component, which is called simulators. And you want to connect the simulator input to the component on your canvas or the components on your canvas that take the longest to calculate. So for us, it's going to be this Caramba simulation. And why we want to do this, you'll see in a second. So now you can double click the component. It's going to load, and then this window with this colorful heat map shows up. Now, if I click in this heat map, my Grasshopper canvas will update. So what this heat map actually is, you can see all these little arrows. I hope that they're not too small for the stream and the resolution. But every arrow here corresponds to one of our input sliders. And all of these points here are points that we have simulated during the optimization. And we use the star coordinate system to map those points on a 2D surface, and we encode their performance with color. So orange areas are good, purple areas are bad, or orange is low value, purple is good, high value, and since we're minimizing, this corresponds to good and bad values. So when I click in here now, like I said, my Grasshopper canvas updates, and if I have a simulation that is not as quick as Caramba, then this might lead to you having to wait 5 minutes every time you're actually clicking in here. But since Caramba is fast, right? You can now explore this known design space. So basically, we have our points that we sampled during our optimization, right? And we have an associated performance that we predict with a machine learning model. And you can see, okay, this says, okay, the expected performance, for example, for this solution is 162, while the actual one is 90. But if we go into areas where there are more points, like here, it becomes a lot more accurate. So right here, we predict 46.2. The actual value is 46.07. And these are also the areas where the optimization found the most points, right? This seems to be an area that is very light. It has almost not exceeded the displacement, and it has very limited structural height. You can also interact with this diagram down here, where again, every arrow is a slider on our canvas. So for example, our slab height should be this. No. Oh, let's see. Yeah, the top one. So our slab height is this arrow. It's basically the dimension that goes up and down in our 2D plot. So I don't know, if I find a solution where I like the column placement like here, and if I now just go up on the surface, this will just increase the thickness. And again, you get the predicted performance in real time. Of course, with something like Caramba, you can do the same thing live, but if you have something that takes a little bit more time to simulate, like daylight or energy, this tool comes in very handy. And you can also start to understand the relationships between your performance and your parameters, right? So, yes. Okay. Looking at the time, I think I went a little too long.
It's okay, don't worry.
Maybe we go to Q&A.
To the questions. Yes.
Yeah.
Excellent.
Yeah.
Many thanks for
Awesome.
the presentation and live demo. I think we
you.
all enjoy it a lot. Well, there is a typical question. What's the difference between Opossum and Galapagos and Wallace?
Yes. So functionality-wise, not so much. The difference is really in the implemented algorithms. And again, I can only tell you what we have observed in a whole bunch of different benchmarks now. Also independent from us, right? There are other research groups that do the same thing. And it seems like on our kind of problems, the model-based algorithms perform better, right? So the difference is that in Wallace, they're using MSGA2. If you can afford 20, 30,000 iterations of your optimization, then this can be a good option, right? If you cannot, then you should use something that is good in few iterations, something like RBF-opt, which is implemented in Opossum.
Cool, thanks. Another one by Jeremy Bamberger. In Mo, so MOO, you mentioned you can weigh certain objectives. If possible, can you show an example of that?
Yes. So if we go, I should share, right? So if we go back to this Grasshopper, oops, sorry, here. So basically, what we've done here is we're only panelizing the volume, right? But I could also say, okay, displacement is very important to me, and volume is not so much important to me, right? Then I could I don't know, multiply. Oops. I could multiply the displacement with something like 0.95 and multiply the volume with something like 0.05, right? So the sum of the weights equals 1, and then I could get the product, again, the multiplication of these two, and now optimize this value. So that is what we mean weighting or a weighted product, right? So this makes sense in our case, right? Because we have this limit, we do not want to exceed a given target. That doesn't make as much sense. This does make sense if both objectives are equal in, like, let's say, to the law, but you just want to steer the optimization, right? So this would take displacement a lot more into account now than volume.
Okay, thanks. This one is from Gabriel Garcia. How to know the order of the input parameters in the results if these were connected automatically?
Very good question. I don't know. You probably don't. Yes, I have never thought of this. Yeah. So
Then take
it's
it as a suggestion. I mean, that's
yes. Yes. So you would have to maintain the log file because this writes the order of names. There would also be the possibility to maintain or obtain it from the component via code, which is of course tricky. That is a very good point, and we're gonna include this. Actually, we want to make this logging, there will be an updated version of this anyways, but this will be included. Thank you.
Okay. And then this is an answer from Jeremy to Paula. Paula, you just perform a 1/x inversion and minimize everything.
Yes.
Yeah, because I think Paula, yes, she was asking, what if one value needs to be minimized and the other maximizes in the same multi-objective optimization simulation?
Yeah, exactly. So quite generally, all optimization algorithms only minimize, right? So they can only minimize. If you choose maximization, it will multiply your objective by -1. And in this same sense, you would do it, right? So let's say, okay, for whatever reason, I want the thickest slab, so I want to maximize the volume. I would multiply this with -1. Oops. And then because of course, the larger this is, the smaller its negative value will be, right? And then you take this. Yeah.
Okay.
Good question.
Then this one is from Chi Yuan 10. How much time consumed will be considered an expensive optimization problem? And how do you deal with the runtime parameters that you want to optimize about?
Yeah. So, I mean, time is tricky, right? Because time also depends on how good your computer is. So, a normal optimization budget would be something like 100 times the number of parameters you have. So if you connect 10 sliders, right, a proper budget would be 1,000 iterations. A small budget would be something like 50 times n, so 500 iterations. And then if then it's up to you. If you can afford to wait 500 iterations, then it's fine. But maybe you cannot, right? Because again, it takes some time and you have only 5 hours until your client meeting. And you can only run, I don't know, 100 iterations. Yes. So the expensiveness is a little subjective, but if you cannot afford 50 or 100 times n, even 50 times n actually, then you should absolutely use some model-based optimizer.
Okay. Can you use GPU acceleration? Osvaldo Belit says that he remembers seeing that or reading about in your expert tab.
Yeah, so unfortunately, no. We're basically, yeah, we have to run everything on the CPU. Yeah.
Okay.
At least
Then
one comment to this, the calculation of the optimization algorithms, this is really not the bottleneck. This is what I want to hint to. So if your daylight simulation, for example, is GPU accelerated, then this is still valid, right? And in our every iteration, the actual evaluation of the optimization algorithm happens in milliseconds anyways. So the bottleneck is usually the simulation. And then, yeah, so this, of course, you could perform on the GPU.
okay. Then this is more generic question from Maha Al-Gebali. How can I use it for paneling or facades?
I mean, so this paper I wrote earlier this year, so if you Google my name, you'll find it. We did actually optimize a facade. So instead of changing the column placements, we had some static shading elements and we changed the geometry of this shading element. And we calculated the energy consumption and the daylight, and then used the daylight and energy consumption as the objectives. But of course, this then, I mean, you can use any type of variable and any type of objective.
Mhm.
Yeah.
Okay, one more by Amat El Tabel. For how long I have to run the optimization? Is there a limited time or I have to stop it manually?
Yeah, so you don't have to stop it manually. You can set the iterations exceed, or the duration in seconds exceeds, right? So if you have 10 minutes, then you can set 10 minutes here. But we don't recommend to do this. We always recommend to set the iterations, and then this will stop automatically, right? And again, you should run it anywhere between 50 and 100 times your the number of input sliders. If you want to find a real optimum, right? If it's more a good enough value, right? If you want to find something good, Opossum can find good solutions within 100 iterations. I mean, you've seen it before, right? We ran it for 60, 80 iterations and we found designs that actually fulfilled our constraints, and were lightweight and didn't affect much.
And is there a limited number of variables to do the optimization?
Yeah, so basically the complexity of the problem increases with the number of variables. So typically you would say not more than 100 variables. This is then already a very, very hard problem to solve, right? So with every slider you add, the longer you will have to run the optimization algorithm, because this search space, right, it becomes just really, really vast, and very complex to navigate.
Mhm. Okay.
Yeah.
Sorry, I missed the second question by Chi Yuan Chen, and he posted here again. It's about how do you deal with the runtime parameters that you want to optimize about?
So I assume it's about the inputs.
Probably it's the runtime parameters that you want to optimize. I can explain more, he's saying. Let's wait for.
Yeah.
Well, in the meantime, that was
Mhm.
a nice question also. Why is it named Opossum?
Ah, um, it's called something with optimization and surrogate models.
Mm-hmm.
Yes, so yeah, surrogate-based optimization or something, and then the sum from the surrogate and op from optimization. I think that's where it came from. So I also didn't really explain this well, but RBF op, the main algorithm in Opossum,
Mm-hmm.
it really builds this machine learning model, a so-called surrogate, and that's where the name comes from.
Okay. Okay. One question from Esther Kleise. Is the penalty component part of a specific package?
And no, I just wrote this in Python. This is really so all this is um, I calculate the distance, which is basically just how far away is my input from the target, and then I either so exponential is to the power of 2, asymptotic is just the square root, and yeah, this is just mm, my stuff.
Okay.
Yeah. You can
Uh,
also, of course, use the Grasshopper native component, right, with the where you can define a mathematical formula.
mhm,
Would do the same.
perfect. And Yasamin Mernia asks, yes, how to find the best penalty function if we are new in learning optimization?
Trial and error.
Trial and error. Okay.
Yeah, yeah.
And participating at the forums, no? Asking
Yes,
other
yes,
people.
yes.
Perfect. Okay. Um, yeah, Chi Yuan Chen um, explained better what he's asking about. He says, I have an optimized problem that related to pathfinding, but not until runtime the graph will not be created.
Okay. Um, Without knowing your problem, there is a different class of optimization problems, which is called combinatorial optimization, right? It's usually yeah, something like the traveling salesman problem, right? Or the knapsack problem. Knapsack is easier to understand, right? So I have a bunch of different things and I have a backpack and I can only carry 10 kilograms, right? And now I want to choose those objects that have the highest value without exceeding my 10 kilograms. So now, I don't know, there's a vase in gold and a bunch of other stuff. Um, my first decision now influences what I can do for the rest of my optimization, right? And these types of problems cannot really be solved with this type of optimization, right? So here we're talking about this continuous optimization. And if you have something that really, I mean, maybe you all know this, I don't know, like the reclaimed timber projects where they put some trees and then they find the next best branch and they put it next to it and assemble like a truss like this, step by step. And these project problems are very hard to solve with like this kind of continuous optimization. And I assume that your problem is like this.
Cool, thanks again. And I'm sorry we are running out of time and there are a few more questions, but I suggest to the audience to contact Max and his team through his website. Also, yeah, Gabriel was also asking, how do you know if there is a new version of the plugin? I guess the package manager tells you about, right?
Yes,
Maybe you are also sending an email to people that download the software
correct.
whenever there is a new version.
Mhm.
And yeah, many thanks again, Max. let
Yeah,
me
thank you,
show you also my
Carlos.
video. It was a
Yeah,
pleasure. It was very instructive. And I hope we will meet soon again. To the audience, also many thanks for making these webinars possible with your attention. And the recorded session will be available between tonight and tomorrow.
awesome. Thank you, everybody, for listening.
Thank you, everybody. Have a nice day.
Bye
Bye.
bye.
Bye.